Hey, hey, välkomna, and welcome to the Design of Embedded and Intelligent Systems, Lecture 2. Today, we'll be talking about requirements. So, of course, requirements, design, implementation, and evaluation are all interlinked. Requirements you can think of as your intended outcome, implementation, the actual outcome, and evaluation where you compare those, and the design will build on the requirements. But I think this is kind of a useful way to go step by step through this, through some of the concepts we want to explore. In this lecture, you're also going to learn some terms maybe, like waterfall, red ocean, gorilla arm, and neats versus scruffies. So if you're interested, you can pause the video now and check out these questions. Otherwise, we continue. So to get started, I've broken down the things that we're going to look at into three parts. Based on the idea that people use a design process to design some type of system, which I'm calling artifact here just because I don't want it to be confusing when we talk about system view. So I'll talk about people, processes, and artifacts. First, people. Who can design embedded and intelligent systems? Anybody can. But this is such a multidisciplinary area that it's very inclusive. There is no one right perspective. So over the years, I've seen researchers working with playwrights, musicians, philosophers, artists, and of course, this includes also gender and nationality and stuff like that. So if we look at the images on this slide, at the top left, this is a theater play with an android robot on the left, a human on the right. And on the top right, this is a Toyota robot that's making music. At the bottom, we have some female roboticists who have been doing really incredible stuff. These aren't the best images, of course, it's just Creative Commons stuff, but we have Rosalind Picard on the left, who is a pioneer in emotions for computers. We have Cynthia Brazil, who is also a pioneer for social robots, designing Kismet and Leonardo and lots of other really cool robots. We have Ayana Howard, who is working in HRI, and she also created products for children with special needs. We have Simone Giertz, who tried to popularize being a maker and making robots, that we don't need to make perfect robots all the time. It's fun just to make stuff. And Catherine Kuchenbecker, who was working with haptics and socially assistive robots. These are just a few examples of some female roboticists, and basically the message is anybody's welcome in this area, regardless of what you do or whatever. Group work. When you design systems, it's impossible to avoid people in groups. You'll have to work with other people. For some, this might even conjure a little bit of a feeling of despair. Maybe you're going to have to do more work. You'll have to do sometimes other people's work, and you won't get any credit for it. There's also some social stress if you have to deal with people who are difficult. So I've had sometimes former students say that they don't want their friendships to be hurt by working together with others, because when you have suddenly lots of work to do and lots of pressure on you, that can bring out sometimes some conflict. And we know about different effects in psychology that relate to group work, such as social inhibition and loafing. This is sometimes called Ringelmann effect, and it relates also to the bystander effect. So if somebody is hurt in the middle of a city, maybe lots of people will just ignore them because they think this is not my role. It's not my task to help right now. And this happens also in groups. However, group work can also be very nice. Small groups can be very effective. And there's effects like social facilitation and compensation. Some of the things that we should think about to try to get these effects to happen. One is that everybody in the group should feel that their role is important and that others are not going to do their tasks, that the responsibility is divided very well. Also, it's nice if there's not so much pressure on people. So there's this effect that if maybe somebody is staring over your shoulder when you're doing some type of difficult task, it becomes more difficult. People also have various biases. One example of that is the actor-observer bias. If you do something wrong once, it might be because you might think that it's because of a certain set of circumstances. You had to do that. If somebody else does it, though, you might think that they're a bad person, and you might not think that it was this set of circumstances that maybe caused that. So it's good to be aware of biases like that. And then I have a few personal recommendations. One is respect. So I once had a misunderstanding at a previous job where my boss thought that I was not so respectful because I didn't say good morning each morning. And actually from my side, I'd said good morning each morning, but I didn't hear it back from him. So I thought he wasn't that type of person and I stopped saying it. Which is sort of an indication that even if you think somebody isn't respecting you back, that you can still try to be respectful to them to avoid misunderstandings. Perseverance, I think, is really important in working in a group. Another analogy from my past, I was working in a group in Canada for my undergraduate, and the groups were usually composed of 6 people. But I was sick on the day when the groups were chosen, and we were just the remainder of the students. There were only 3 students in my group, and at the end, the other 2 students left. They didn't show up for the final examination. I was there by myself, and the teachers let me get by with a 50%. And I was able to raise that a lot with the other part of the course, which was an exam. So I was able to pass and still do okay. So I recommend being persistent and not giving up. Empathy, of course, is important to be able to see from another person's perspective, to try to understand what exactly they want, why they maybe want something. Communication, I've seen in some of my previous students that they often don't see other people in their groups when they're working on their projects. And then many different students have to ask the same questions, or they don't, and they just don't know the answer. And then there's this mismatch in knowledge and a mismatch in expectations, which of course is very, can easily lead to conflict. Okay, so then we've talked about people, and the next thing that I'd like to talk about is basic strategy for designing stuff. So please pause the video now if you want, and I'd like you to think, what is the difference for you between engineering and science? What is the difference between research and development? These are sort of basic things that we have to consider when we're designing a system. Okay, so I guess you've paused the video if you wanted, and now you have an answer. My personal answer is as follows. Of course, I think there is no one right answer. This is, people define things in different ways, but this is my answer. Science for me is when you try to understand a phenomenon, so you form a hypothesis and then you test it. This comes from Greek, meaning splitting or discriminating. For me, basically, this is, if you use the scientific method, it's science. In engineering more, the emphasis is that you've got some type of problem and then you build a system to overcome that problem. This word comes from Latin, from cleverness or to devise something. Then we look at research and development. Research, when you talk to academics, is not usually like just looking something up in Wikipedia or in a book or something like that. It's more talking about original research, that's creative work undertaken on a systematic basis to increase knowledge, which can include development as well. So I think there's two important things that I've highlighted here. One is creative and the other is systematic. So creative should be new, but not crazy. It should be something still useful. And systematic, we should follow valid ways of thinking, be methodological. Development, technical work which is not new, but can be useful or required. So when you're designing your system, is it going to be, are you looking to do some science? Do you want to do engineering? You can think about this. Next, another thing that we are usually always concerned about is, are we going to be done on time with a good result when we're trying to design a system? And there are many suggestions on how we can try to go about doing this. So I've got two suggestions on this slide. On the left, I've got a sequential type of method called waterfall. On the right, we've got an iterative incremental method called agile. So on the left, waterfall, what is it? It means that basically you go step by step through this, through these four aspects. Requirements, when you're done with that, you go to design. When you're done with that, you go to implementation. And the good thing about this is that early changes cost less. So you get a really good idea of what you're going to build, and then you build it just once. That's the idea. Documentation is also produced early. I wrote exists with a question mark here because I'm not actually sure that this really fully exists in a pure form in the world. I think in any case, if you are developing a system and you see a problem, you might go back and try to fix that. Okay, on the right, we've got something called iterative and incremental development. Iterative means that we're going through the cycle more than once. Incremental means that maybe you start with a simple system, just a few features, and then each time you iterate, you'll make it a little bit more powerful and complex. So this kind of thinking has been around since the 50s. Agile was something born in the 90s as sort of a reaction to these heavyweight kinds of projects where there's a lot of micromanaging. And what they said basically was that we can't plan for what we don't know yet. And it's basically, producing lots of documentation. Documentation is very useful, but it's not the main point. The main point is the product that you're developing for the customers. It's the people. So the good points with Agile is that it can deal with unforeseen problems. It's fast, and you always have something to show. Even if your money is cut all of a sudden halfway through, you got something. And this is always the method that I'm using when I'm doing research with little prototypes. It's always an iterative thing. So there are many, many different suggestions, strategies that are maybe slightly different. Big design up front is a little bit on the side of waterfall. It's more that you want to really think things through before you start to build. And then that is very valid for certain contexts where it can be very expensive to build. Front-loading design, you prepare things for a family of products rather than one specific product. So for example, it could be a line of different models of cars that you can create at the end. Concurrent development model, basically you get started in all of these four areas at the same time. You're working on your requirements while you're working on your testing, etc. Spiral, You're iterating and choosing stuff to work on in order of risk. Scrum is also from the 90s. It was you have daily stand-up meetings and you have sprints, sort of these short phases where you work on some type of plan, like can be two weeks or a month or something. DevOps, this is an idea of extending agile style thinking to an organization. And there's no end to these. So I've written a few in green from the students in this course. You don't have to remember this. Extreme programming is another one that it's the sprints are shorter than in Scrum, and you can change them while you're in the middle of one. Test-driven development, you should try to immediately go from your requirements to ensure that they're testable. Yeah, and there's many more like that. So another way to look at things is from a top-down or bottom-up perspective, and people define these also in different ways, but I always look at it in this way. Top-down is what is the most important problem that we want to solve. Bottom-up is what can we do practically with the tools that we have. And then both ends against the middle, in my opinion. This is the most typical in reality. We of course are constrained in the things that we can do, but we are also interested in what problems exist. So it's balancing those two. Now, the problem with all of these suggestions is how can we scientifically assess what is good and what is bad? A company or a group of developers or designers doesn't want to take a strategy that they think from the start is not as good as another strategy. So it's very difficult to compare and say, this is better than this one. And finally, for looking at the basic strategy when you're designing a system, you want to also think what type of technological readiness level is desired. So on the left, you can design prototypes. You can design a low fidelity, mid fidelity, or high fidelity prototype, where the low fidelity prototype, it can be just like a visual depiction of your system, website or a robot or whatever, just a cardboard mock-up or something like that, or it can have some type of functionality, some type of limited functionality. This type of prototype is very cheap, but when you show it to users, the feedback that you get might not be perfectly accurate. On the other side of the spectrum, if you make a high fidelity prototype, it can be quite accurate. It looks exactly like the product that you want to design, but it can be quite expensive in time and money to prepare that. So NASA has come out with a system of technology readiness levels that you can see on the right. So I've heard, though, that companies sometimes define these levels in different ways, so there can still be a little bit of miscommunication. But basically, at the bottom, we've got prototypes and research, and then at the top, it's really finished products. Okay, now we talk about your systems, your artifacts that you're designing. We need to have sort of a list of specific points that we want to address, because otherwise, if we don't have a clear idea, it's how can we solve it? We need to specify what our system should do and how it should be. And to do that, we can look from various different perspectives. So one thing to consider is the timing. What do we want to do in the long term? What do we want to do in the midterm? And what do we want to do in the short term? Another thing that we can look at is what positive features should our system have? And what are the negative things that we want our system to avoid? And another thing is, what should the system do and what type of content should we have? So for example, if we have a robot, then we might want our robot to say something when the user presses a button. That's system. And then what the robot should say, that can be contents. So we can just swap that out. We can create different contents, swap it out. One really useful thing to look at when you're defining requirements is if they're functional or non-functional. A functional requirement is what the system should do. For example, the robot vacuum cleaner should do my housework. Non-functional requirement is how the system should do it. Should the system be safe, reliable? So non-functional requirement is more related to your system architecture, the higher level view of your system. Functional requirements are said to be more related to the lower level design. Yeah, and then you can also go an extra step and prioritize your requirements. So you can compare pairs of requirements when you've created your list, requirement 1 versus requirement 2, which one is more important? You can also get multiple judges to look through each requirement and rate it like on a scale from 1 to 5, and then take the average. If the standard deviation is low, then you have a good amount of agreement about the priority of a certain requirement. And now when you have your list of requirements, you also need to look at them from a system perspective. Systems are very complicated, and there's different things that you should be aware of as potential pitfalls. Systems are inherently interdisciplinary, and they're also holistic. So here is an example of dependency. It's very common if you're building a robot that the motors and batteries are dependent on one another. So for example, if you want to give your robot a stronger motor, then maybe you need a bigger battery to supply the current, but then the robot gets heavier and you need a stronger motor again to drive it. So when you're considering changing one aspect, you have to think of the other aspects as well. Another thing to think of is trade-offs. Often you just can't have everything that you want. So this is a well-known set of trade-offs. For example, if you want something that is fast and cheap, then it probably won't be precise. If you want it to be fast and precise, it'll probably be expensive. Another thing to think of right from the start is that your design should be participatory. That means you should think of what are the different stakeholders who are involved, and you should involve them early on. So there's a well-known example from interface science about the gorilla arm effect. And the story is that the designers created a system without enough user feedback. And when they wanted the users to use the system, which was a touchscreen, a vertical touchscreen, they found that the users had to hold their hands in sort of an uncomfortable position for many hours, and they got very tired from using that. So the moral of the story is that you should involve different groups when you're designing. Designers don't always know exactly what the users need, and the users often don't know what they want on the other side of things. For example, if you're designing for people with dementia, they can't be expected to tell you what algorithm you should use for the robot that they should interact with. They don't know. Systems can be very complicated. We have these chaos effects, right? With the butterfly flaps its wings and something changes on the other side of the planet type of thing. Emergentism, we have sort of unpredicted effects that emerge when we combine different things. So for example, hydrogen and oxygen are gases at room temperature, but when we combine them, we don't get a gas, we get a liquid at room temperature. And this relates also to how we look at our design space, do we want to look at a simplified version of our problem and then try to find the best solution possible? So maybe some math equation that perfectly defines this simple problem. Or do we want to look at the more complex problem, but then just try to get something that's good enough that works for that? So there are terms to describe people that think in these two groups called neats versus scruffies. These are terms from MIT. The neats are the ones who want to do a perfect math solution. The scruffies just want to solve the problem. One interesting category of problems that we can look at from a scruffy point of view is something called a Fermi problem. A Fermi problem is something that seems really, really complicated and impossible to answer at the beginning. But if you actually make some simple approximations, you can get sort of a reasonable answer to this type of thing sometimes. One of the famous examples is how many piano tuners are there in Chicago? But we can say the exact same thing, like how many students have studied robotics in Sweden? And then to guess the answer, we can just look at how many universities do we have in Sweden? And how many robotics programs are there? How many robotics courses are in those programs? How many years have they been teaching robotics? And we can get some type of approximation, a back of the envelope calculation type of thing. Another thing that we can think of when we're looking at our requirements is, will we create a sustainable system? So it's sustainable development, and we can look at perspectives like ethics, environment, and economy. Here for ethics, I'm showing three properties of a system that have been described as common properties in AI systems that could actually hurt people. So they're opaque, we don't know how they work, damaging, they have really an important effect. They could maybe get people fired or something like that. Unbounded, this set of algorithms can be easily scaled or applied to a different group where it shouldn't be applied. And these are from Cathy O'Neill from her book, Weapons of Math Destruction, which is a very interesting read, I think. Environment, we can think from two different aspects. We can think, are the parts that we're using environmentally friendly? Or we can think, could our system do something to help the environment? If it's a robot, for example, could it clean up plastic waste from the oceans? Could it put out forest fires? Could it help with agriculture? Economy. This is, of course, also super important, and you can have different perspectives from the economical side as well. From the research perspective, what are the estimated cost savings? Can we help lots of other people that we can't help right now? From the other side of things, we can look at products. How can we, will people actually buy this thing? Will we actually be able to exert an impact on society? Are the parts inexpensive enough? So this is a big issue with social robots. We have such high expectations from the research side, but when we compare a social robot with something like a home assistant, it's costing maybe thousands of dollars more just that this platform can wiggle its arms or something. It's just not enough that people will actually spend the money. So we have often companies have problems when they try to release social robots right now. Okay, so this is then most of what we wanted to talk about today. We have now a list of initial requirements, and we want to know how to define our system. How can we do this? We'll talk about it in the next episode. So before I go, we'll also go over the questions that you saw at the beginning of the lecture. What is waterfall? Waterfall refers to software development cycle. Red ocean refers to an area red from blood due to cutthroat competition as opposed to maybe a blue ocean strategy. Gorilla arm refers to fatigue from using a touchscreen. The short message is involve your stakeholders early on. Needs versus Scruffy describes seeking perfect versus approximate solutions. So thank you very much for listening. And then for anybody who's interested, I'll talk a little bit about Sweden. I came to Sweden in 2014 because I had a really nice image of Scandinavia. I thought it would be sort of safe and interesting cultural wise. What did I think when I got here from Japan? Some of the fun impressions I had were that the traffic lights were a bit like machine guns. They really sort of push you to cross the street fast. They rattle away. The doors and windows can be very heavy. My wife had trouble opening sometimes our windows. There's a song that is sung at midsummer called Little Frogs, which actually comes from a French national song from the time of Napoleon, which was quite interesting. We had really nice offices at our university where the tables could go up and down. That was kind of cool for me because in Japan, it was an open office type of environment. And so some suggestions if you're in Sweden and you want to see some fun stuff, I would say the old town in Stockholm is quite popular, and there's also lots of nice islands there. Oslo was a really fun, nice city. You can see all these Stavkirken, this sort of ship like a Viking ship, these churches that are shaped sort of like a Viking ship, and the fjords and all this if you go a little bit north. Lots of snow all of a sudden. Varberg, there's a nice castle. Gothenburg is very close to Halmstad. Gotland in the east of Sweden is a beautiful island where the capital of Visby is also very beautiful. They used it to create a well-known Japanese animation, this scenery. Kalmar has a nice castle. There's also these stores like IKEA and Ullared around here. Ullared is a very big store that sells lots of stuff cheap. They even have a TV show about this in Sweden. Denmark is very close by. There's Elsinore with Hamlet's Castle and Copenhagen. Kiruna on the north, you can see beautiful auroras. I didn't know that it would actually be so beautiful, but when you see a great aurora, it's really actually very impressive. Lithuania, Finland, Estonia, Latvia, Poland, Germany, there's lots of places near here. Over here, you can see a picture of Saint Lucia's celebration. This is a Swedish thing where you have these costumes with candles on people's heads, which can be a little bit interesting. This is the midsummer celebration over here. The salmon is very tasty, and we have very nice beaches here actually. Okay, that's it for me today. See you next time.